we went through examples 1 through 5, talking about the first derivative to find increasing, decreasing, and maximums, minimums. Next thing I want to talk about is the second derivative. So this is kind of a new piece. With the second derivative, we know a derivative tells us like if something is increasing or decreasing, right? So it's basically telling us if the first derivative is increasing or decreasing. In terms of our original graph, that actually gives us what's called concavity. If we look at these, you notice how this graph is curved upward? So like if you continued that graph, it would hold water, right? That's what we call concave up. When it's curved like this, if you continue that, water's just going to go off the outside, so it's curved downward. That's called concave down. The second derivative gives us that, because if we think about the slopes of these tangent lines, if we look at those tangent lines, they're all positive slopes, so they're increasing. But if we did the second derivative, those are increasing faster with time, so it would be positive as well, so it's concave up. If the second derivative is negative, it's called concave down. So if we look at this one, like the first derivative would be positive because the graph was increasing. But if you did the second derivative, if you look at the slopes of these lines, they are getting flatter. They are decreasing with time. So the second derivative turns out to be negative. So on your little fill in the blank thing, the first one says if the second derivative is greater than 0, and so what you need to write in the line, that means concave up. It's curved upward. If the second derivative is less than 0, that means it's concave down or curved downward. So let's look at an example. So this figure shows a population of honeybees. At what rate of population, how does the rate of population increase change over time? So if I'm looking at this, can we agree that the population is increasing as we go on? Okay, but can you make any more comments about that? It starts out, this section is concave up. Would you guys agree with that? And then somewhere in the middle we switch, and then what happens? It's curving downward. So what that's telling us is at the beginning, was it increasing more at the beginning or the end? Where was this increasing the fastest? Let me ask that question. Kind of started out slow, and then it picked up, it jumped really fast, and now it's starting to flatten out again. So we can make comments like that if I'm just asking how does the population increase change over time. So the rate is low at first, and then gets faster, and then slows at the end. Second question I asked, when is the rate the highest? When does this seem to have the fastest jump in population? What do you think? Like the steepest part of this graph? Say like this area is the steepest. Would you guys agree with that? So maybe between 10 and 12 would be a good approximation. That's just asking when the graph jumped the fastest. That's the steepest part of my graph. So concave upward and concave downward. We already kind of talked about that. We said it kind of switched right about here. So it started out concave up. So we're just going to say from 0, because we wouldn't have negatives, to roughly 12. And then after 12, what happened? It was curving downward. And we don't really know when this ends. That point in the middle, like our 12, when we change from concave up to concave down, that is called an inflection point. So an inflection point is really just the critical point of the first derivative, but anywhere where you change concavity is an inflection point. So, a couple ways to use this information. There is a second derivative test. I don't really like this one, and I don't really use it a whole lot. I really like the first derivative test. I think it's very obvious. If you go from increasing to decreasing, you have a maximum. If you go from decreasing to increasing, you get a minimum. The second derivative test is another way to decide if it's a maximum or minimum. To me, it's kind of unnecessary because if you're going to do a second derivative, don't you have to do the first derivative anyway? So we already have that information and we can use it. But it tells us if the first derivative is positive, or is 0. So if the derivative is 0, that means it could be a maximum or minimum, right? So if you have an x or min, and the second derivative is positive. If the second derivative is positive, what does that tell us? It's concave up or concave down? Concave up. So we have a max or min, but if our graph is curved upward, then it has to be a minimum. If the first derivative is 0 and the second derivative is negative, that means it's curved downward, so you get a maximum. So it's just another way of determining if your critical point is a max or a min. Another downside of this one, sometimes when the first derivative is 0, the second will also be 0, and then this won't tell us if it's a maximum or a minimum. So go ahead and give it to you, throw it out there in case you like it. But when I work problems, I'm usually just going to do the first derivative test to decide if things are max or min, because it always works, and we don't have that case where it doesn't. So let's look at an example. I want to draw a possible graph that meets all of these conditions. So I have a ton of conditions here. Let's figure out what all of them mean. So the first condition tells me the first derivative is positive. If my first derivative is positive, what does that mean? Well, the first derivative is positive. Just think back yesterday. If the derivative is positive, what does that tell us about our graph? It's increasing. So we know that right now. So it's increasing until we get to 1. So wherever x is 1, so maybe here. Okay. So we're increasing until we get to there. And then the first derivative is negative, so it's decreasing after 1. Okay, so I have a lot more to determine, and I'm probably going to have to adjust my graph as I go, but right now all I know is it's going up and then going down. So what's going to happen at 1? If you go from increasing to decreasing, you have a max. Okay. The second derivative, ooh, I have a typo. How about second derivative is greater than 0? Sorry about that. So the second derivative is greater than 0 until I get to negative 2. And if the second derivative is greater than 0, what does that tell us? It's concave up. And after 2, the second derivative is negative between those, so it's curving downward between them. Okay. So negative 2 and 2 are what we call inflection points. They are places where the concavity of our graph changes. Usually on my graph, I kind of mark those with an X. I don't know Y values, but I know we're going to change here and then at 2 again, so maybe here. the limit as we go to negative infinity is equal to negative 2. So as my graph goes forever in the negative direction, it's equal to negative 2. So let's see if we can draw this half of the graph. We know it's increasing. We know until I get to negative 2, it's curved upward. And we have to be getting closer to our asymptote, so curving upward. And then after I get to that point, we're curving downward. We have a maximum at 1. Okay, with the limit as we go to positive infinity equals 0. We're still curving downward, we're decreasing, and then we switch to curving upward, and we're getting closer to this. So if we check back through our requirements, increasing until we get to 1, decreasing after 1, concave up until we get to negative 2, concave down between negative 2 and 2, concave up after. Horizontal asymptote, as we're going in the negative direction, is negative 2, and as we go in the positive direction, is 0. Alright, so do you kind of see how the concavity changes there? It's not like a drastic change, but just a slight change in the curvature of our graph at those inflection points. I'd like to do an example just finding the concavity. So finding when a graph is concave up or concave down. In order to find that, what do we need? Second derivative. Okay, so our first derivative would be what? Then the second derivative would be we need the inflection points. Inflection points are just like critical points, except you're doing it on the second derivative. Is this derivative ever undefined? No. So we just need to find out when it's 0. So we get x equals 1. So that is what's called an inflection point. That is where the concavity of our graph changes. And so to find the concavity, it's just like finding maxes and mins, except we're doing it for the second derivative. So we're going to do that sign line. The point where we change is 1. Since we're looking for concavity, we're looking at the second derivative. So test points. If you put in a 0, you get a negative. If you put in a 2, you get a positive. So that tells me my graph is concave down, where the second derivative is negative. So negative infinity to 1. And it's concave up, where the second derivative is positive. So 2 to infinity. So it's exactly like what we did yesterday with maxes and mins, except you're doing it for the second derivative. So when we're looking at our sign line, you're plugging them into that second derivative here. Yes? We need a test point bigger than 1. Oh, oops. 1. Sorry about that. Other questions? Okay. Let's do an example that uses everything. So I want to look at this function, and I'm going to find all the things. Concavity, inflection points, maxes and mins, and I'm going to draw a graph from it. So first thing, we need our derivative. So that would be 4x cubed minus 12x squared. Okay, if I'm going to find maxes and mins, what do I need to do right now? Right, find our critical points, anywhere this is 0 or undefined. So if I set this equal to 0, take out a 4x squared. So we get x equals 0 and 3. Those are my critical points. What do we do with that? We make a sine line. Okay, we need a test point smaller than 0, in between 0 and 3, bigger than 3. And where are we plugging those in? The derivative. Okay, so we can put them in the original, the factored one, especially if you're not using a calculator, it's probably easier to do the factored one. 4 is positive, negative 1 squared is positive, negative 1 minus 3 is negative, so that would be, if I put in a 1, 4 times 1 squared is positive, 1 minus 3 is negative, and a positive times a negative is also negative. We talked yesterday that most of the time the sign changes. This time it didn't. Why? When you have squares on one of your critical points, that's usually when you're going to get the same thing twice in a row. 4, if we plug it in, 4 squared is positive, 4 minus 3 is positive, so that section is positive. Okay, so this tells me several things. It tells me, first of all, where I'm increasing and decreasing. Where is my graph increasing? Where is it decreasing? Negative infinity to 3. Okay, it also tells me maxes and mins. At 0, I was decreasing, I continue decreasing, that's nothing. But at 3, I was decreasing, then I switched to increasing. So what's that? Local min. You can give me function notation or an ordered pair. When you do that, where are you plugging that 3 into to get the y value? The original, because I want the point on the actual graph. So 3 to the 4th is 81. So negative 27. Okay, so that's kind of yesterday's portion. Now, we've got our maxes and mins, but we need inflection points and concavity. So what do we have to do? Second. Okay, so I go back to my first derivative. I would do the one before we factored it. So that derivative is 12x squared minus 24x. And inflection points are where the second derivative is 0 or undefined. So if we take out 12x, that would leave us with x minus 2. So we get x equals 0 and 2. Those are the inflection points, places where the concavity might change. So how do I check my concavity? Sine line. So this is all involving the second derivative. So we do our test points, and we are putting these into the second derivative. Okay, if we put in a negative 1, we get a negative 12 times a negative 3. So negative times a negative is positive. If I put in a 1, I get 12 times a negative 1. So positive times a negative is negative. If we put in 3, we have a positive times a positive, which is positive. So, where is your graph concave up? Union. Where is the graph concave down? All right. Have I lost anybody? We want to be able to put all of this stuff on a graph. Inflection points, if we're going to mark them on the graph, it would be helpful to have ordered pairs. How do you get the y value? Plug them into the original. So if I put in 0, we get 0. If we put in 2, 16 minus 32, so negative 16. minimums on my y-axis. Now we plot all of our stuff. So we know we had a minimum at positive 3, negative 27. Inflection points, I'm going to plot those with x's. So they're not maxes or mins, those are places where the curvature of our graph just changes. All right, so we know our graph starts off decreasing. Okay, so it is falling. And it is concave up to begin with. So my two options. You can be falling like this or falling like this. If you're concave up, it's the first one. Okay, so we're falling, but slight curve upward. Now, between 0 and 2, I'm still falling until I get down to my minimum. But now it is going to be curved down. So it's not like you have a crazy change in your graph. It's very subtle, something like that. And then after that, I am curved upward forever. Okay, so I'm going to change my curvature again, come and hit my point, and then we have to stay curved upward, but now my graph is increasing. So it would be like this. Okay, this is a polynomial, so your graph is a curve. You shouldn't have a bunch of corners. We're not looking at zigzags or anything like that. And it's a function, passes the vertical line test. So just kind of check those things over at me. Are there questions there? I'm stopping here today. I want you guys to practice